Hello, welcome to our webinar on Science Meets AI. I'm Flora Zhu, a sophomore from Great Neck South High School, New York State. I'm a student volunteer for the Planet+AI program. I'll be your moderator for this webinar. Our invited speaker today is Josh Nguyen, a PhD student at the Department of Computer and Information Science, the University of Pennsylvania, where he works with Duncan Watts at the Computational Social Science Lab. He is also a visiting student at the Mathematics and Computer Science Division, Argonne National Laboratory. Josh is intrigued by the understanding of developing computational and human-in-the-loop methods to study individual and collective human behavior. His other interests include mathematical optimization, especially in the context of machine learning. Recently, he has been studying the capabilities of foundation models in areas involving the generation of novel and specialized knowledge. The problems he is pursuing include hypothesis generation in astronomical research with Yuan Xintin and the Universe TBD Consortium, and evolution of language models in various scientific contexts. This event is supported by the National Science Foundation and also by the Tennessee Space Consortium at UT. Josh Nguyen from University of Pennsylvania will talk about Science Meets AI, lessons from the exploration of large language models in astronomical research. This talk will trace his recent study in large language models. Josh, would you please share your full screen?
Sure.
All right, I'll give it to you.
Thank you. All right. Can you see my screen now?
Yeah.
Okay, thanks. Yeah, thanks again for the introduction, Flora, and thanks, Ping, for inviting me to this webinar. First of all, I'd like to say that I expected this to be a meeting so that people can unmute themselves and ask me questions. But since a lot of you in the audience are not allowed to do so, and I might not be able to monitor the whole Q&A thing, I'm probably gonna have to ask Flora to help me with questions. So if there's any question you want to ask me during my talk, feel free to interrupt, and I'm happy to address them. Okay. All right, so I'll get started. So my name is Josh, and I'm a first-year PhD student in computer and information science at the University of Pennsylvania. Again, thanks for having me. So my talk today is titled Science Meets AI, Lessons from the Exploration of Large Language Models in Astronomical Research. Over the last 6 months, I have collaborated with many computer scientists and astrophysicists on a mega project on hypothesis generation in astronomy using large language models. So in this talk, I will describe our efforts so far and engage in a discussion with you on what can be done when we apply this framework to other fields such as Earth and planetary sciences, more familiar with you, I believe. All right. So I'd like to think we're living in a very exciting time for artificial intelligence, especially in the scientific context. We have a very impressive digital collection of papers, materials, and other informal documents related to our scientific research efforts. In addition, artificial intelligence research has come up with a wide range of methodologies to model this data and extract useful information in patterns that can be used for many purposes. This is coupled with the proliferation of specialized hardware for AI, such as GPUs and high-performance computing systems. So all of this has facilitated very impressive AI systems, as we all know, such as AlphaFold in biology by Google DeepMind, MedPalm in medicine by Google, and many chatbots that can analyze a range of human behaviors and characteristics. And this is only to name a few. What is interesting is that more than ever, scientists around the world can obtain access to these systems, helping them accelerate many scientific workflows that would have been impossible otherwise, and hence contributing to the democratization of science. We've seen a huge increase in interdisciplinary collaboration between people from a range of traditional scientific fields coming together and solving ever larger and more pressing problems in science. I want to first start with an introduction to the architecture behind most artificial intelligence systems these days. We call it the sequence model. When applied to human language, it is given a more familiar name, language model or large language model if it is large. So this model is trained in what's called a self-supervised manner. Specifically, the model is supplied with a sequence of words and is tasked with predicting what word comes after it. In this example you're seeing on the screen, we're having a partial sentence. This paper introduces a new language. And the model is asked to predict what the word what the word coming after this would be, right? For example, it's quite likely that the word model fits in this context, language models. But also another word such as technique or resource might be also likely to come after this. So if a model is trained in this particular manner, this is called a causal language model. And it basically is the backbone of most language models that are very popular these days, including GPT-4 and Gemini by Google. The key, however, to having very impressive models is to train them on lots and lots of data. Latest models, such as GPT-4 and so on, are trained to complete trillions of sentences, of sequences like this. And the data they're trained on is typically taken from the entire snapshot of the internet. That's why they can have trillions and trillions of words and sequences to train on. Okay, this seems easy, but why are these models interesting to us? You know, to some of us working on computer science and astronomy, um, you know, it started when we interacted with these large language models, specifically on our domain of expertise, that we realized something very interesting is coming up. So on the right-hand side, you're looking at an example that my colleague Joe Shuta and Yuan-Sen Ting presented recently when they played with GPT-4. The model seems to do a very good job of summarizing one of Joe's papers with quite remarkable accuracy. It seems promising to use large language models like this to assist us with, navigating the vast literature of scholarly astronomy as a result. So we asked ourselves this question: what does this mean for astronomy? Many applications come to mind. Large language models can help us to summarize research articles, find relevant papers through information retrieval systems, generate interesting hypotheses based on the existing literature, and many more. Large language models are, however, not without limitations. It doesn't take you too long to find out that while ChatGPT seems very versed in answering a range of generic questions, when it comes to highly specialized domains, it is especially lacking. In astronomy, however, this can be a serious lack of scientific accuracy, a phenomenon which we call hallucination. Most language models are trained to complete texts from a statistical point of view, but few of them are explicitly trained to respect certain facts that are essential to scientific publication. Hallucination can also be attributed to the fact that language models are trained using a very large corpus of texts, and research papers only occupied a very, very tiny portion of this collection. The most effective way to address this issue is through fine-tuning, which I'll explain later. Our work is actually not the first to use large language models for astronomy. The first work to explore language models is actually in 2021, in which the authors, Grazies and others, proposed to fine-tune the popular BERT model. It's probably the most popular model about a few years ago, to fine-tune that model on an astronomy data set. So the resulting model is AstroBERT. So, however, about 3 years has passed, a lot has changed since then, especially including the availability of many, many larger, more capable and open models, and also data sets. So our first work, which I'll explain in the next slide, aims to build upon AstroBERT's foundation and to offer a new model with much wider downstream applications. So let's talk a bit more about fine-tuning, the focus of our first paper. As I explained earlier, large language models are statistical models trained to recognize patterns in text. In particular, they are trained using an extraordinary amount of data taken from the internet, and this process is called pre-training. Fine-tuning, however, on the other hand, refers to the process of adapting a language model to some specific data set for a downstream task. This task can be text classification, clustering, regression, similarity calibration, among many others. Through this process, we benefit both from the pre-trained model's general performance because it was trained on so much data, right? As well as the application-specific performance of the model via fine-tuning using our specialized data. In astronomy, we are quite well positioned to achieve this thanks to many open data sets and the availability of a lot of language models, as I explained earlier. Going a bit into more detail, we describe here two main ingredients in fine-tuning in order to achieve our model. First, we start with a pre-trained model on the left-hand side. We choose Llama 2, which is a model, a large language model by Meta AI, and it was released in July 2023, I believe. This model contains about 7 billion parameters and was trained using 2 trillion tokens taken from the internet. Meta AI has demonstrated that it performs really well on a wide range of tasks, and most importantly for us, unlike a lot of other models, it is actually available for us to use. The second component is a data set. We need a high quality specialized data set. Fortunately, we have the archive paper repository, and what we did was extract all papers categorized under astrophysics, which I think total about 300,000 papers. We then extracted the abstracts of these papers, leading to a final data set of about 95 million words. And then similar to the pre-trained model, this data set is also available. Finally, once we have the pre-trained model and the specialized data to fine-tune it on, we use Llama 2 and fine-tune it to achieve a new model, which we called Astro Llama. Okay. In particular, Astro Llama is used to predict the next token of an astronomy abstract. Okay. This task, as I explained earlier, was called causal language modeling. Right. And compared to the base model, Llama 2, Astro Llama achieves about 30% better perplexity score. And this score is a metric for generative models, and lower means better, better fit to the data set, or 30% in this case is quite a substantial improvement. To examine Astro Llama's capability, we ask it to complete several astronomy papers abstracts given a short prompt. So here's an example. I won't go too much into the detail, but I'm happy to refer you to the paper so that you can read it later on. But it's essentially what we did was we prompted GPT-4, the base model Llama 2 by Meta, and our model Astro Llama with the first few sentences of an original abstract, and then we tasked them with completing the rest of the abstract. Okay? GPT-4 is currently the state-of-the-art in language modeling, generally speaking. We, however, find that its completion is actually quite too generic and off-target, even though it sounds quite natural and coherent. Llama 2, the model by Meta, typically gives a short and quite off-topic continuations in a lot of cases. But when we look at the continuations by Astro Llama, it actually exhibits quite remarkable context awareness in its completions, and by showing quite a deep understanding of quite a lot of astronomical concepts. Second, we test Astro Llama's ability to embed text in the astronomy literature in a meaningful and semantically consistent way. So text embedding refers to the process of mapping a paragraph, a paper, or just a piece of text in general to a vector in a high-dimensional space, Euclidean space in particular, such that the text or the paragraphs that are similar semantically speaking are embedded close together in the embedding space. And those that are different in meanings should live far away from each other. Okay. So we begin by taking 10,000 randomly chosen abstracts from our data set, and we embedded them using two models, our model AstroLlama in red and GPT-3 in blue. Okay. So the plot you're showing at the top left shows the distribution of pairwise cosine similarities between abstracts, okay, where the higher similarity on the x-axis, okay, refers to or corresponds to papers that are more similar semantically speaking. Okay? So as you can see in this plot, with GPT-3, most papers are actually judged to be very, very similar to each other. With cosine similarities are all around 0.7 to actually to above 0.9. On the other hand, the similarity scores produced by AstroLlama, which are depicted in these red curves, are much more diverse, much more dispersed, suggesting that it's embedding a quite nuanced representation of the semantic content. When we examine specific examples later on, we find that the similarity scores by AstroLlama are actually meaningful. So in here, I'm giving you two examples. So let's take a look at the example in pink. We have two papers, and GPT-3 judges the two papers to be very similar. So they're about 78.5% similar, right? But in fact, these papers are actually not similar at all. And our suspicion is that, this similarity probably stems from the common word that is present in both papers, the word magnetized, which seems to be a linguistic heuristic signal that it's trying to exploit, okay? Incorrectly, of course. AstroLlama, on the other hand, successfully distinguishes these two papers and says that the papers are only about 36% similar, so very small. Okay. The example in teal also illustrates a similar point. Okay. AstroLlama calibrates the similarity score between the papers much better than GPT-3 when these papers are actually very, very similar. Okay. Even when these papers actually don't have any common words to match. Okay. So that's AstroLlama. It is a large language model that is adopted from Meta AI's Llama 2 architecture, which was pre-trained using, AstroLlama was fine-tuned using 300,000 abstracts in astronomy articles on arXiv. Okay. Our first work so far shows that supervised fine-tuning works, and it works pretty well. However, we don't just want to complete an abstract. We don't just want to feed the model a partial abstract and ask it to complete it. What we actually want of a model is to interact with us. It should respond appropriately when we ask it things like, here's a paper, summarize it. Tell me about the main findings of this work, or what direction hasn't this paper pursued but should have? Okay. Which leads us to step 2, adapting our model to conversations. The goal here is to continue to train or fine-tune the model, but now using a data set that contains instructions or conversations instead of just raw abstracts. An example training instance would look something like this. Here's a paper, and then the paper. Summarize the paper in 5 sentences, followed by a 5-sentence summary supplied to the model. So this summary can be written by a human, for example, the author or the reviewer, or it could be given by another model, right? We then use this data containing the prompt, the instruction, and the responses, right, to fine-tune our model further so that it recognizes conversations and responds in a more appropriate way. Okay. In particular, we start with our fine-tuned AstroLlama model in the first paper. To curate conversations, we use the same arXiv dataset, and we extract every paper's abstract and also introduction and conclusion sections, right? Then we feed the abstracts, introductions, and conclusions to GPT-4, prompting it to digest the paper content and generate candidate questions and answer pairs from this paper. The result is a paper plus a list of questions and answers generated by GPT-4. We also augmented our dataset with a few other open instruction datasets common in natural language processing. And then we continue to fine-tune our AstroLlama model on this new conversational dataset, the result of which is a new version which we called AstroLlama Chat. The weights of AstroLlama Chat have been changed to reflect the conversations it's supposed to imitate. We also perform a qualitative analysis of AstroLlama Chat in which we ask it a series of very, very specialized questions in astrophysics. These are questions posed by my collaborators who are actual physicists and not myself. So I can I can probably help you debunk a few things, but not a lot. But the idea is we gave it a bunch of questions that are like, how many dimensions are there in the elemental abundances of stars, right? The results we get that suggest that AstroLlama Chat does a much better job of answering these types of questions, much better at least than GPT-4, the state of the art, and Llama 2 Chat. The Llama 2 Chat is Meta AI's chat version of Llama 2, which was fine-tuned for a bunch of everyday conversations. All right, so let's do a quick recap of what's been described so far. We started with an open language model, Llama 2, by Meta AI. We then adapted this model to astronomy, the astronomy domain, by performing supervised fine-tuning using about 300,000 abstracts on arXiv. We curated a list of questions and answers from these papers to further tune AstroLlama for conversational capability. You can actually play with these models online on Hugging Face. There are some challenges, however, that still remain, and we are investigating a lot of them, and we're dedicating a lot of effort in addressing these challenges. First, the instructions were actually created automatically by GPT-4, remember, which is quite problematic because these questions and answers did not go through any vetting by humans, so we don't know whether they're actually true or false. Most of them are true, but we never know. We actually don't know how much of them is actually incorrect. AstroLlama Chat, therefore, can inherit these potential errors in its downstream generations. The second challenge is that our ultimate goal is to take advantage of the model's creativity. How do we make it generate interesting and worthy hypotheses, for example? And third, how do we ensure that the model's behavior is trustworthy and safe to the extent that users won't be able to force it to output gibberish or actually harmful or misleading content? Right? So regarding the first direction, we are organizing a large study involving the curation of content, both from humans and AI, an effort which we call human-in-the-loop content creation. This is to ensure that the instructions we give to models are fully vetted by experts, which will have tremendous consequences for models when it comes to synthesizing complex scientific content in a more faithful way. The second area we're exploring concerns knowledge-intensive generations. This is especially important in science, where we want content given by models to be accurate and traceable to previous publications, for example. Imagine you ask AstroLlama to tell you what is worthy of exploration when it comes to topic X in astronomy, for example. What we wanted to do is to look into the literature, find what has been done in X and what has been discussed accordingly, and then suggest worthy directions later on. The reason we want to have this literature at hand and not just relying on the parametric model in itself is because we want its generation to be based on established results that are traceable to our knowledge base. So this is an example of what's called knowledge-intensive generation in natural language processing, where the results of models must be based on quite a large knowledge base that may not be able to be encoded in the model's weights in any particular way. Okay. And finally, we are looking into cases in which we don't want a model to behave as usual. For example, no one wants ChatGPT to tell people how to make a bomb, right? Similarly, we don't want models to output information that is false or not backed up by our scientific data. An example of hallucination that I mentioned at the beginning of the talk. One way to address this is to align a model with human preferences. The idea is to have a model output several candidate responses and have humans rank them in terms of, say, acceptability or accuracy. The ranking signal is then fed back to the model to adjust its behavior accordingly. You might have heard of the term called reinforcement learning from human feedback, and this is one example of such an RLHF. All right. So to conclude, I have described what we have a lot at hand. So we have a lot of data in the format of text, images, videos, and a lot more. We have a lot of compute power. Well, to an extent, we are not as rich as Meta AI or OpenAI or Microsoft, but we do have compute power to fine-tune language models for our particular domains, right? We also have pre-trained models released by these AI companies, right? And they are available for us to download and adapt however we want to our data sets. And also, we have domain experts. In our case, we have astrophysicists who work with us along the way uh, in data curation, in model evaluation, and a lot more, right? And so all of that, right? All of that has allowed us to build pretty interesting systems. Most recently, Astrolama Chat. We've got a lot of people reaching out to us saying they have very interesting conversations with Astrolama Chat, and they've also used our model Astrolama to study a range of problems in astronomy that they have data for, right? But there are things that we haven't explored, and this is probably going to be very interesting future directions. For example, we haven't really explored multimodal models. So models that are able to process texts, images, videos, time series, data, and so on. And in a lot of applications in astronomy, this is very useful, especially if you are able to combine what you have for text and what you have for images, right? In addition, we would like to also demonstrate the actual real world usefulness of our system, Astrolama and Astrolama Chat, via a realistic workflow of an astronomer and see how much it actually helps them when it comes to their scientific workflows, right? And that concludes my presentation today. Thanks.
Thank you, Josh, for your amazing presentation. We enjoyed it a lot, and we have some questions in the chat. So let's move on to the Q&A part. So the first question is, how do we measure the accuracy of a fine-tuned LLM?
All right, very good question. So let's go back to this example. So Astrolama, for example, was a fine-tuned version of Llama 2 based on astronomy abstracts. And the way that it's fine-tuned is called supervised fine-tuning, which self-supervised fine-tuning, which means the labels that we use as supervised signals to train these models actually already live in the data. And so when you're trying to predict the next word in, say, an abstract, you're looking at, for example, the accuracy or the cross entropy of your prediction of the possible words that follow a piece of text versus the actual word that lives in your data set. And so a particular metric that we use to measure the performance of a large language model in self-supervised fine-tuning is perplexity, which tells you how well can model predict the next word. So yeah, the perplexity is a metric that is commonly used.
Okay, thank you. The second question is, What exactly do we do for fine tune? Say, use the domain dataset to train models. Could you please specify that?
Yeah, so to fine-tune a model, so you would start with a pre-trained model, right? The model that's released by companies, for example, OpenAI, Meta AI, Allen AI, so on. These models are pre-trained in the sense that they are adapted to a wide range of text, so trillions of tokens taken from the internet and many other sources. And they are versed in a lot of tasks, but when it comes to specialized tasks, they're not that good because they're very well versed. And so to fine-tune such a model to our specialized data is to do continual pre-training, if you think about it. So we follow the same process of predicting the next token, and we train the model to predict the next tokens in our corpus of astronomy abstracts, right? So it through that particular process, which looks exactly the same as pre-training, by the way. Through that particular process, we are aligning the model or adapting the model more to our literature of astronomy abstracts. Uh, it might perform worse in other cases. So, for example, if you ask such a model to complete, for example, a news article, it might not be as good anymore compared to Llama 2. But if you ask it to complete an abstract, an astronomical abstract, um, it tends to do a much better job.
Okay, thank you. Josh, thank you again for your amazing presentation. Thank you all for joining us today, and I hope to see you again on our next webinar.
Thank you. Um,